Hello students, welcome to EPG Pathshala. I am Dr. Manjula Sharma from University of Delhi. Today we are going to discuss about the module Qmeter and Meggers from the paper Measurements and Instrumentation. From this module, students may get to know about the following topics. First, we will learn about Q factor, or in other words, the quality factor of an electrical circuit. We will learn about Qmeter, which measures the quality of passive electrical elements and circuits. Next, we will study the Q measurements by measuring impedance, in which we will study the series scheme and the parallel connection scheme. Towards the end, we will study about the Meggers, in which we will cover the operation of Meggers and the continuity tester. The quality factor is a very important factor in electrical and electronic circuits and components, and it is generally denoted by Q factor. It is an extremely significant factor for the individual components. For an ideal inductor having zero resistance, the quality factor is said to be infinite and is defined as Q is equal to omega L by R. For a capacitor with no leakage, meaning no resistance, its Q factor is given by Q capacitor is equal to 1 by omega C R, which is again infinity. Q measurement is relevant to the measurements on the tuned circuits, as is understood that power in all permeating parameters. In all kinds of circuits such as AC, DC, tuned, non-tuned, AF, RF, power requirements need to be estimated for various aspects, including design, commercial viability, special application areas, and so on. Power factor is defined as a parameter which is determined usable power and is different from the part that is reactive in nature. So students, now let us start with the Qmeter. The quality of passive electrical elements and circuits is measured by Qmeter. The basic principle is to produce resonance with the element connected as required with a dual or complementary element and excite the scheme with variable frequency oscillator. The Q factor of the element is defined as the ratio of its reactance at resonance to its loss parameter or resistance. The voltage drop across the element at resonance is Q times the applied voltage. Also, mod of XL is equal to mod of XC at the resonance. The circuit scheme of a meter is shown in the figure, which consists of an ideal capacitor C for the measurement of the Q factor in a lossy inductor L. Its loss resistance is being indicated as capital R. The figure 1 shows the circuit for Q measurement with vector diagram. If the current through the circuit at resonant condition is I, when XL is equal to 2 pi I FR L and XC is equal to minus I by 2 pi FR C, where FR is the resonance frequency, then It follows that voltages across the capacitor and inductor are equal in magnitude and opposite in phase. Net output voltage is given by VO is equal to IR, being the same as the input voltage VI. If a voltmeter connected across the capacitor shows Vc is equal to Ixc, then Q of the inductor coil is Q is equal to mod of XL by R is equal to mod of Xc by R is equal to Vc by Vi. As Vi is known, the voltmeter indicating Vc is directly calibrated in Q factor. Voltage Vc is obtained by varying frequency of the oscillator when the indication becomes maximum. It must be kept in mind that if the capacitor has a leakage resistance and the oscillator output resistance is non-zero, which should be negligibly small with respect to R, then the indicated Q is slightly different from the actual value. Further, the stray capacitance, especially at high frequencies, causes change in the effective L value and hence the Q factor. The interwinding capacitance of the coil behaves similarly. Students, the frequency at which resonance occurs is given by the relation F is equal to 1 by 2 pi square root of LC. This is a well-known relation. However, in practical situations, the same relation is adopted to suit the conditions of operation and measurement. Actually, the practical measuring schemes are slightly modified, mainly because of the measuring uncertainty in the value of Vi. A small shunt resistance is supplied by the oscillator, which acts as the source of the circuit. The voltage across the shunt resistance VSH becomes the multiplying factor then. For wide frequency ranges from 0.05 to 500 MHz, a thermocouple meter is used for measuring VSH. The oscillator is provided now with a variable series resistance for adjustment of VSH. Tuning is done by oscillator frequency or by varying the capacitor. Now students, let us study the Q measurement by measuring impedance. Two different schemes of Q measurement are proposed depending upon the nature of the impedance measurement. These are the series connection scheme for low impedance and parallel connection scheme for high impedance. First of all, let us consider the series scheme. The figure shows the circuit for Q measurement by measuring impedance in the series scheme. If the low impedance components are to be measured, which have, say, low resistance, low inductance and high capacitance, the series scheme is used. Figure shows the series scheme, which consists of a low resistance Z1 placed in series with the work coil supplied with the instrument. The measurement is done in two steps. First, Z1 is shorted by a strap S and the circuit is tuned by varying C to a value C1. The Q1 indicated by the voltmeter becomes the reference. Second step is where Z1 is brought into the circuit by opening S. C is tuned to a new value C2 and Q2 is obtained in the voltmeter. If R is negligibly small, we get 1 by omega C1 is equal to omega L and Q1 is equal to omega L by R, which is equal to 1 by omega R C1. In the second case, the reactance of Z1, that is X1, is given by X1 is equal to 1 by omega C2 minus omega L, which can be written as 1 by omega C2 minus 1 by omega C1. So, the simplified expression for X1 becomes C1 minus C2 divided by omega C1 C2. Also, the resistive part in Z1, that is R1, can be found from the two measurements as follows. The circuit resistance for the first measurement is given by Rm1 is equal to Xm1 by Q1 and Rm2 is equal to Xm2 by Q2, giving us R1 is equal to Rm2 minus Rm1, which can be written as Xm2 by Q2 minus Xm1 by Q1. Putting in the values, we get R1 is equal to 1 by omega Q2 C2 minus 1 by omega Q1 C1. So, the final expression for R1 is C1 Q1 minus C2 Q2 divided by omega C1 Q1 C2 Q2. From these equations, it follows that if C1 is greater than C2, X1 of Z1 is inductive, whereas if C1 is less than C2, X1 is capacitive. Also, for a purely resistive Z1, C1 is equal to C2 and R1 is equal to Q1 minus Q2 by omega C2 Q1 Q2, which in turn is equal to Q1 minus Q2 divided by omega C1 Q1 Q2. Students, now let us study the parallel connection scheme for the Q measurement. Parallel connection scheme is a circuit used for high impedance measurement and is shown in the figure. Initially, the high impedance is isolated by the switch S and capacitance C1 and Q value, that is Q1, noted for resonance with the essential working coil. Then ZH is brought into the circuit parallel to C and the coil, and returning is done to obtain C2 and Q2. Here again, for the first measurement, 1 by omega C1 is equal to omega L, and Q1 is equal to omega L by R. Thus, the value of Q1 is given by 1 by omega R C1. With second tuning and measurement, omega L can be written as x C2 multiplied by xh whole divided by x C2 plus xh. The value of xh is equal to 1 by omega C1 minus C2. If xh is inductive, LH is given by LH is equal to 1 by omega square C1 minus C2. And for capacitive XH, CH is equal to C1 minus C2. Parallel resonance also indicates that total circuit resistance RT is given by RT is equal to omega Q2L, which in turn is equal to Q2 by omega C1. Further, from the circuit, 1 by RT is equal to 1 by RH plus 1 by RC, where RC is the resistance of the working coil, which is given by RC is equal to Q1 by omega C1. So that 1 by RH is equal to 1 by RT minus 1 by RC. Putting in the values, we get 1 by RH is equal to omega C1 by Q2 minus omega C1 by Q1. So, the final value of RH is equal to Q1 Q2 by omega C1 multiplied by Q1 minus Q2. From this, the Q factor of the unknown impedance is obtained as QH is equal to RH by XH. Putting in the values, we get QH is equal to Q1 Q2 multiplied by C1 minus C2 whole divided by Q1 minus Q2 multiplied by C1. The shunt resistance RSH across the oscillator produces appreciable error in the measured value of Q unless RSH is negligible with respect to coil resistance. In direct connection shown in the figure, if RSH is percentage of R changing to R multiplied by 1 plus A by 100, then the Q factor changes by delta Q, which is equal to Q actual minus Q indicated. Thus, delta Q is equal to 1 by omega C whole multiplied by 1 by R1 minus 1 by R into 1 plus A by 100. Simplifying the expression, we get delta Q is equal to 1 by omega CR whole multiplied by 1 by 1 plus 100 by A. If A is 0.01, error in Q is 100 delta Q by Q actual is equal to 100 by 1 plus 100 by 0.01, which is approximately equal to 0.01%. For A equal to 10%, error in Q becomes 9.1%. So students, now let us study about the Meggers. The Megger is an instrument used for the measurement of high resistance and insulation resistance. Essentially, the Megger insulation tester consists of a hand-driven DC generator and a direct reading through ohmmeter. It consists of permanent magnets which provide the field for both the generator and the ohmmeter. The moving element of the ohmmeter has three coils known as current or deflecting coil, pressure or control coil, and compensating coil, which are mounted rigidly to a pivotal central shaft and which are free to rotate over a stationary C-shaped iron core. The coils are connected to the circuit by means of flexible leads or ligaments that exert no restoring torque on the moving element. Hence, the moving element may take up any position over the scale when the generator handle is stationary. The current or deflecting coil is connected in series with the resistance R between one generator terminal and the test terminal marked L. The series resistance R protects the current or deflecting coil in case the test terminals are short-circuited and also controls the range of the instrument. The pressure or control in coil in series with a compensating coil and protection resistance R is connected across the generator terminals. Compensating coil is provided to obtain better scale proportions and to make the instrument astatic. When the current from the generator flows through the pressure coil, the coil tends to set itself at right angles to the field of the permanent magnet. With the test terminals open, corresponding to infinite resistance, no current flows through the deflecting coil. The pressure coil thus governs the motion of the moving element, causing it to move to its extreme counterclockwise position. The point on the scale indicated by the pointer under this condition is marked infinite resistance. The current coil is wound to produce clockwise torque on the moving element. With the test terminals marked L and E short-circuited corresponding to zero external resistance, the current flowing through the current coil is large enough to produce enough torque to overcome the counterclockwise torque of pressure coil. This moves the pointer to its extreme clockwise position. The point on the scale indicated by the pointer under this condition is marked zero resistance. When a resistance under test is connected between the test terminal L and E, the opposing torques of the coils balance each other so that pointer comes to rest at some intermediate point on the scale. The scale is calibrated in mega ohms and thousands of ohms so that pointer indicates directly the value of resistance under test. The guard ring is provided to shunt the leakage current over the test terminals or within the tester itself to the negative terminal of the generator without passing through the current or deflecting coil of the instrument, and thus eliminates errors due to it. Usually, a terminal known as guard terminal is provided by means of this guard ring, may be connected to a guard wire on the insulation under test. The test voltage is generated by the generator G, which in many portable sets is driven by the means of hand-operated crank. The higher test voltages are used in the instruments with the higher resistance ranges. Variations in generator voltage in a given instrument do not appreciably affect the readings unless the apparatus under test has considerable capacitance. To avoid the effect of charging and discharging currents which are due to variation in applied voltage, special type of sleeping clutch is fitted to the handle so that the generator speed and output voltage remain constant even when the handle speed is variable. Since the same magnet system supplies for both instrument and the generator, the instrument indications are independent of magnet strength. The operation. The resistance under test is connected between the test terminal L and E. The generator handle is then steadily turned at uniform speed. In the case of the tester fitted with a special type of slipping clutch to the handle, the speed is controlled by the centrifugal device. The turning of the handle must be kept up until the pointer gives a steady reading. The larger the capacitance of the object under test, longer it will take to charge and give a steady reading. Students, at the end, let us see the continuity tester. The continuity tester is an instrument used for checking the continuity of circuits, that is, for determining by resistance measurement whether given circuit such as the inner conductor of a cable or a run of steel conduit has good conducting capacity throughout its length without a complete or partial break. Unlike Meggers, this also consists of a hand-driven DC generator and a low resistance reading ohmmeter housed in one case. It is usual to have continuity scale to read up to 100 ohm or so. The scale is open in the low range so that values up to 1 ohm are easily read. Since this is the most important part of the scale from the point of view of continuity measurements. If the resistance under measurement is very low, the voltage drop across the deflecting coil circuit is low and very little current flows through it. Therefore, the pointer is deflected in the same direction as infinity on the insulation scale to the point marked 0 on the continuity scale. On the other hand, if the resistance under measurement is high, the voltage drop across the deflecting coil is increased. The current through the deflecting coil is increased. Therefore, pointer is moved to the other end of the scale. So students, let us summarize what we have learned in this module. In this module, we studied about the Q factor of an electrical circuit. We learned about Qmeter, which measures the quality of passive electrical elements and circuits. Qmeters are based on the principle to produce resonance with the element connected as required with a dual or complementary element and excite the scheme with variable frequency oscillator. We also studied about the Q measurement by measuring impedance. Two different schemes of Q measurement have been proposed depending upon the nature of the impedance measurement. These are the series connection scheme for low impedance and the parallel connection scheme for high impedance. Both the schemes have been studied in detail and with derivations. Then we studied about the Meggers, which are instruments used for the measurement of high resistance and insulation resistance. We studied about the operation of Meggers and continuity tester. Thank you.